Okay, it's 4 o'clock. We're going to get started. So this is Physics 211 Recitation. So once a week, it is optional. I'm going to go over this first recitation. Since last Wednesday was snow day, ice day, whatever you want to call it, we didn't have it. So I'm going to go over a little bit about what we're going to do in here. That'll take about 5 minutes. And then I'm going to do what I'm going to tell you I'm going to do. So typically how this works is I'm going to have a lecture portion, a portion that I talk about something that Jason wanted to talk to you about, but didn't have time for, or something like that. Then I'm going to go over problems that Jason wants you to know that he also did not have time for. That might be 1 or 2 problems. I'll probably limit it to 2 problems so that we have time at the end for any type of homework questions or anything like that that you want to go over. So the only part that's not going to be every week is part 3. So I'm going to do lecture, a problem, and then demonstration. I might not do a demonstration. I'm not going to do a demonstration today, but Jason might want to do a demonstration in class or lecture that he doesn't have time for. So this is basically an overflow. It's things that he wants you to know that he didn't have time to talk about. And typically that's stuff that will help you on the test. So keep that in mind. Just a couple notes. Oh, and then after questions and answers, if you don't have any more, then I'll probably just start doing problems, random problems. But for the most part, you can ask questions throughout this recitation at any point. Just know that homework and question and answer is later. So try to ask questions that pertain to whatever I'm doing, not something else. And then the other part is that this will go until 4:50. So it's a 50-minute recitation, and then we're done. So I'm going to start off. The first thing we're going to talk about that Jason wanted to talk to you about but didn't have time. This is a really big book. When I took this class, it was 6th edition. So in 7 years. So it's like once every 2 or 3 years. They come out with a new edition, which is ridiculous because classical physics doesn't change. So why should they have a new book? I don't know. Okay, first thing we're going to go over is page 45. Page 45 talks specifically about, and you don't have to open it if you don't want to, but it talks about general problem solving strategy. He wants to make sure that you've set up the problem in the correct way, that this can actually help you in a lot of situations to figure out how to solve the problem. I guess before I start, were there any questions before I begin? The other thing is that if you have labs on Thursday, I'm most likely your TA for labs as well. I teach 11:30 to 5:30. So if you have a Thursday lab, then I'll be your TA as well. Just keep that in mind. Okay, so general problem solving strategies. There are 4 things that you kind of have to do. I did it slightly different than this when I was an undergrad. I guess I should tell you my name at least. My name is Kyle Martin. I'm a 4th year grad student. My research is in, technically it's theoretical exobiophysics. So I look at things on other planets and try to model living things on other planets. Kind of cool. And that's all I really want to tell you. Okay. So the 4 things are conceptualize, categorize, then there's analyze and finalize. So it's just a bunch of I's. Conceptualize meaning you have to think about the problem, think about what it's about, think about a lot of different things. You have to understand the problem. That's the point of conceptualize. The categorize is you want to see if this problem relates to other problems. Is this a simple plug and chug problem? Is it just easy to do? Is it done? Game over? Or is there something else you have to do? Is it more analytical? Is it going to require more time? So that's categorize. You have to know kind of what it's like, what that problem is going to be like, how much effort that's going to take. The third one is analyze. This is the part where you're going to be trying to figure out the problem. You're going to be trying to actually get the solution. That's in the analyze part. And then finally, finalize. This is a part where you ask yourself, does this answer make sense? Do the units make sense? Do all these things make sense? That's pretty much what finalizes. Okay, so conceptualize says you have to start with two things. You have to think about the problem and understand the situation. So the very first thing you need to do when you're looking at a problem is try to understand what it's telling you, especially if it's like some story problem. It has like 10 sentences and you're like, there's no picture, like what the heck is going on? Figure that out first. That's the first thing you need to do. After that, if there's no sort of picture provided, sketch one. So I know Jason today in class was like, make sure you sketch a picture. So I know he's talked about it at least a little bit. Make sure that you have some sort of picture sketched out, you understand the situation. I feel like a picture is actually one of the best ways to know how a problem is going. It's also, as a teacher point of view, it's really easy to understand if the student knows what they're talking about. If they draw a picture and they say this is what's happening, then I'm like, okay, they knew what was happening, they just missed this. I'll take less off because I knew they understood it conceptually, they just implemented it incorrectly. So a picture is always a good way to get a little bit more points if you can. So just make sure you always have a picture, understand the picture. The next step, after you got the picture, make sure that you understand the information it's giving you. This can include things like initial conditions. If it says at initial time, at time 0, this is where it is. This is how fast it's going. Write all those down. There's several different notations you can use for position. Position, you can write x initial. You can write x naught. You can write x and then a 0 in parentheses. All those mean the beginning, the very first position of the entire system. That's the beginning. And then if the problem tells you that, then you can say this equals, and then give the number. So whatever that equals. If it gives you velocity, make sure you write down the velocity. Don't just assume that you'll know it. Write it down. Write down the velocity, write down the acceleration, write down everything it gives you, and write down some things it doesn't give you. If it says a ball is falling, well, then the acceleration is going to be equal to negative 9.8 meters per second squared. It's a given. It's not explicitly told in the problem, but it might be things that you should know already. So make sure you write down everything. Even if it doesn't pertain to the problem, just write it down. If you think it's even a fraction of a percent of a chance that it will help you, write it down. Later on, you're going to eliminate everything that doesn't make sense to use. But at the very beginning, just write down everything you can. This will help you a lot in problems. Just write down everything. So after you write down everything, try to figure out what exactly the question is asking. So after you have the knowns, so this will be your knowns, try to figure out what unknowns you need to figure out. So there might be, find the acceleration. Awesome. A equals question mark. Write it down. I don't know what it equals, but it's in my unknown section, so I know I need to figure it out. If you get to the end of the problem and you haven't found all your unknowns, you're not done with the problem. So make sure that you are specifying what you need to figure out. Now I should, at this point, I guess I should have said this at the beginning, but I could also say at the end, but I'll just say it in the middle. You might not have to do this exact setup for every single problem. 4 plus 5 equals 9. Did you use any of those? No, there's no need. It's too simple. You don't need to use these for every single problem. This is specifically for problem solving, problems that you don't know, hard problems. This general setup is going to help you figure out any sort of problem, whether it is 4 plus 5 or not. But just know that it may not be required for every single problem. Okay, so you have your unknowns listed. You don't know what the unknown. Okay, so your last one for conceptualize, last idea of thinking about it, try to think of what a possible answer could be. If you are asked, what is the speed of this car? There's no way it could be 1,000 meters per second. That is just way too fast. You would kill your stick figures in your drawing. It's just way too fast. So you have to limit your answers. Your answers can't be anything. You might think, oh, it's a question mark. It can literally be anything. Yes, I guess that's true. But physically speaking, it cannot be. There's limitations. Not always will textbooks, I don't know, they won't always adhere to these general ideas. Like I did one problem where there was actually like 8 or 9 G exerted on a person, and I'm like, that would kill the person. There's no way that could be the real answer, but it was. But typically, you will get answers that make sense, like 99.9% of the time. So make sure, so the fifth part, I'm not writing these down because they're in your textbook, but the fifth one is think about what a reasonable answer should be. So that is conceptualize. At this point, you should understand the problem, understand what you have, what you need to find, and what a normal answer would look like. Are there any questions about conceptualize? Okay. The next part is categorize. We need to figure out what this problem is. One of the best ways to do this in undergrad is to compare it to other problems that you've had. So if you have a problem, especially on a test, if you have a problem, it's like, figure this out, figure this out, figure this out. You can be like, oh wait, I've done a problem similar to this. How did I set this problem up? You're categorizing. Now, there's a couple ways to categorize it. One is a simple plug and chug. And what that means is you're given all the unknowns and you know the equation right off the bat. So let's say it's some sort of figure out the x final. So there's different ways to write that too. I usually do xf, x initial plus v initial times t plus acceleration, assuming 1/2. Assuming acceleration is constant, that's what you get. And then you're like, okay, we just have to figure out x final. Well, I'm given all of these. So I can just plug everything in, get the answer. That's a simple answer. That, in fact, the book calls a substitutional problem. I call it plug and chug, because you're literally just plugging it in, chugging it. You get the answer. That's one way to do it. However, if you're given, if you do this equation, it's like figure out the acceleration and the position. Well, now you can't just use one equation. You have to use maybe 2 equations. Depending on how many unknowns you have, you might have to use multiple equations. So this is the part where you should be able to determine how you're going to solve the problem. This is your categorizing part. Now, at this point as well, you can actually start removing, if you remember the knowns and the unknowns, you can start removing what you do not need. You're like, well, the problem is asking for this, and it's a substitution problem. I don't need any of these. I got the answer done. I don't know if Jason does this, but sometimes professors will give you more information than you need. And that will sometimes confuse you, because you're like, I'm not using this thing. I feel like I need to use this. I feel like it's important. Not always. If you're doing the categorizing part correctly, you should know what you should and shouldn't use. So make sure if there's a similar problem that you just solve it that way. If it's similar, sometimes he combines 2 problems. Just think about it that way. Categorizing is fairly straightforward. Are there any questions about that? Okay. Now, the important part of analyzing. I actually had a professor that we didn't even have to get the right answer. We could just analyze it correctly and he'd give us full credit, even if the answer was wrong. Now I'm going to tell you how that worked, but at this point, you're going to list out every equation that you need as well. So if it's not a substitution problem. If it's not a substitution problem, you're going to start listing out the equations you need. I need this one, I might need this one and this one. I need equations. Especially on a test when you do not have, I guess, an equation sheet. If you don't have an equation sheet, first thing I do is I sit down, I write out all the equations I can remember. In fact, I actually won't answer questions. I will just read the question and write down equations I think the question will need. I literally just go through the test writing down equations, and then I go back and I start solving them. I mean, there's different strategies for everyone. This is kind of a general overview. But But once you have all the equations and everything that you think you need to solve the problem, you're actually not going to start plugging stuff in yet. There are different ways to do this. I would encourage it this way. If you have all the equations, solve for what your unknown symbolically, meaning keep all the letters and just solve for the acceleration. So you have two equations that you need to combine, solve for acceleration without putting anything in. If you have that correct symbolically, and then you plug all the numbers in and get it wrong, there's a much higher likelihood that you'll get more points because you did it correct symbolically, you just plugged something in incorrectly. But if you look at the equation, you're like, that equation is correct. They just missed a number or decimal or something. So it was just the substitution part that they didn't get correct. But everything else was correct up to that point. So the symbolically, I'll go over what symbolically is when I give an example problem. But basically, you just don't put any of the knowns into the equation yet. Now, after that, and then you can plug and chug. Okay, so then we're going to finalize it. Finalize is you're going to you're going to examine. You're going to examine your answer. You're going to compare it to what you thought was viable. So I thought it was going to be between 5 and 10 meters per second. Is it? Yes. Okay, so it's an answer that makes sense. Is it the correct answer? I don't know, but it makes sense. Make sure you look at the units. A fancy name for this is numerical analysis. So people say, oh, I was just doing some numerical analysis. All that means is you're looking at the units. Just like, do the units make sense? If it's acceleration, is it meters per second squared? Okay, so you have the right units. If it's acceleration and it's meters per second, you did something wrong. Go back, go through, see where you messed up. This is super important. I still do this in grad school. I am fourth year in grad school, I'm still doing numerical analysis, and I'm still messing up in parts. And I'm able to fix it because I analyze my units. So make sure that you do that too, and there is a really good chance that you won't mess up. Now, just make sure that the answer makes sense. So some other things that it says in the problem, which I don't know are necessary for most questions, but in the general problem solving strategy, it asks, why was this problem assigned? I don't know if Jason would be happy if you're like, hey, why did you give us this problem? This is a dumb problem. But you could kind of think almost every problem that a teacher assigns, unless the teacher is just completely, just does not care, will usually have some sort of impact on the test. So make sure that if you're doing a hard problem and you're looking at it and you're analyzing it, make sure that you know why it was assigned, what concept was assigned. There's a homework assignment. Actually, I don't know if I can talk about that because I don't know if it's due yet. Oh well, I'll just not talk about it. I grade some of your assignments, and answer some of your questions. But it was about sig figs. And there are certain concepts of sig figs that he wanted people to know. There was a lot of people that missed it. And So just make sure that when you do the problem, make sure you understand why you got it wrong or why you got it right. Both are equally important. Why did I get this wrong? Why did I get this right? Make sure you understand. Okay. So that is basically it for the 4 parts. Analyze, finalize, and then conceptualize, categorize. Are there any questions about problem solving, general problem solving skills or strategies? Okay, so let's do a problem. This says it's problem 222, but it is not. It is problem 228. I'm going to go through and we're going to use our problem solving skills to solve this problem. And hopefully this will help you because I think the weekly assignment's due Friday, right? Okay. I hope it's not this question that's on the test or the homework. If it is, free answers. Okay. I don't know why I'm favoring the right board, but I am. So the problem reads, a truck covers 40 meters in 8.5 seconds while smoothly slowing down. Smoothly always means constant. So if you ever see a question that says smoothly or any sort of synonym to that, it means constant acceleration. To a final speed of 2.8 meters per second. Find its original speed, find its acceleration. Well, that one's easy. It just basically told us what we need to do. So if we were to do this based on the problem-solving strategy that I just went over, what is the problem asking? What is the idea of it? Well, you have this truck slowing down. We don't know what the initial velocity was. We don't know what the acceleration is. So, so we need to find acceleration. It's constant. And v, I'll use not. I'll keep it how I've been doing it. The initial. So original speed. So not chapter 3 yet, so we don't have to worry about vectors. Just find velocity. Okay, so let's sketch a picture. So you have a truck. I usually just do boxes for cars because I'm a terrible drawer. But you have one car. It's going over here. That change shape. And here. This would be your t equals 0. Let's do t equals t initial. And t equals t final. Now, the position is x equals x initial, which we can define. I don't know if it defines it or not. No. But we are going to define as 0.00 meters. And then the velocity, initial, unknown. So I'm actually combining steps, if you're noticing this. I'm drawing the picture and putting my knowns and putting my unknowns. Then x over here equals x final, which equals 40 meters. All right, 40 meters. And then the velocity over here equals 2.80 meters per second. And we need to find acceleration. So what is the acceleration? Okay, first thing I can think of is it's slowing down. So what is the acceleration going to be, above 0 or below 0? Below 0. It's going to be negative. It's slowing down. Now, it can't be too high because it covers 40 meters. Goes to a velocity of 2.8. I actually don't know. I'll say it's between -2 and 0. It's going to be between -2 and 0. Can't be too high. Velocity. Let's see, velocity. So it can't, I don't think it'd be higher than 30 meters per second. And the reason why I don't think it's that high is because that's about 70 miles per hour. And I don't think it could stop and go that slow in 40 meters. So I'm going to say it's between maybe half that, 15 and, well, it has to be above this. I'm going to say it's between 15 and 3. That's a good guess. Let's say it's between 15 and, that should be a dash, 15 and 3 meters per second. Okay, we did our first part. So we've conceptualized it. Make sure that it makes sense. Okay, acceleration can't be too high. You don't want to be pushing G's on someone, so it definitely can't be above 9. And it can't be too hard. It can't be too high because it's not a lot of distance. I mean, it's only 8 seconds. Oh, I didn't put that. 8.5 seconds. 50 seconds. And then we'll define this as 0.00 seconds. Okay, so from that, we've done the entire conceptualize. So categorize. So this problem it seems like it is a combination of two problems. We have constant acceleration. At least we know it's constant acceleration. There's actually examples in your book. I don't remember the exact example, but it's examples with a constant acceleration, and it gives a bunch of equations. And so all those equations are fair game. In fact, let's see, where are you? No, it's before that. So if you want to look at it, it is section 2.6 on page 36, analysis model, particle under constant acceleration. Well, that's what we have. It's smoothly, so it doesn't jump around. It's a straight line for acceleration. So we have equations for acceleration. We have a question for velocity. We have distance, final. So one of the parts, this is not going to be a simple substitution problem. I can tell you right off the bat. Main reason is there's two variables that you're looking for. So it's going to be an, what do they call it? An analysis problem. So we're actually going to have to do stuff. Dang it. So it's going to be an analysis problem. Got that. There are some things we can further assume. We can assume we can ignore friction. There's no coefficient of friction, so I'm going to ignore friction. Any part of friction. There's a lot of stuff with rolling friction and all this stuff. Just ignore it all. No air resistance. So we can simplify the problem a lot. In general, until you get to the part where it talks about friction, I don't remember what chapter that is, you can probably ignore friction, unless told that you can't. But I'm going to ignore friction. Let's see, what else can I do? So I think that's it for categorize. I know that it's going to be a particle under constant acceleration. I know it's not a simple substitution problem. So let's go to 3. Let's go to our analyze part. So the equations that I want to use, I need an equation that figures out initial velocity. I need an equation that figures out acceleration. So I know of one equation I could use. It's actually in that section. So in section 2.6, equation 2.16. This is an equation for position as a function of time. So we have something as a function of time. Okay. So let's do x initial. Sorry. X final equals x initial plus b initial t plus 1/2 gt squared. Not g, not g. We do not want to accelerate that fast. That is a 2, looks like a z, but it's 2. Okay, so now I need one more. Why do I need another equation? Can you tell me right now why I need another equation? 2 variables, 2 unknowns. If you have two unknowns, you always need 2 equations to solve that. So another very simple equation, v initial equals v final plus acceleration times time. These are 2 equations. That one is equation 2.13. So I used equation 2.13 and equation 2.16. This is 2.13. And I knew that because I knew it wasn't a simple problem, but I knew that it was constrained to the particle under constant acceleration. I knew that. It has to be. So now I have this. So now we're going to solve for A from this equation. And we're going to plug it into here for A. because I want an equation that's completely symbolic. So A over there is going to be A equals, and this is wrong, V final minus V initial. There we go. V final minus V initial over T. Yes, and then X final. We're going to solve for VI because that's our unknown. So VI equals X final minus X initial minus 1/2 AT squared all over T. Did I make any mistakes? I occasionally make mistakes. I hope you guys can see it all. I didn't write extremely big. Now we plug A into A here. VI equals X final minus X initial minus 1/2 quantity V final minus initial over T, T squared, all divided by T. Boom. I think. Oh, did I switch those? No, I didn't. I moved VI over. Okay. Did I make a mistake? Anyone? I don't know. Sometimes I make mistakes. I want to be corrected. Okay. So this is our symbolic answer for part A, for velocity. We can now plug and chug. We have every single one of these. XF is 40, XI is 0, VF, oh wait, VI. Oh, I messed up there. This one right here. Okay, well, I don't really want to solve for that because that would probably take too long. Basically, I have a VI there that I'm not supposed to have. I need to move that over to the other side as well, or else the equation's messed up.
What is VF equal to VI plus acceleration time? Oh, VI, like,
Yeah. I don't know, do you guys want me to solve this one correctly? This isn't the completed form. The main problem with this one is I have VI on the other side. I guess I can solve for that. Okay, let's distribute T through. So we have XF over T minus XI over T minus 1/2 VF VI, or just that. VF minus VI. Distribute that through and add this over. So we have 3/2 VI XF minus XI over T minus 1/2. Oh, that's a plus. 1/2. 1/2 minus VF. And then times by 2. That actually might be an equation. XF minus XI minus VF. Okay. Is that an equation? Not quite. It's close to some of these. There we go. But this equation, there we go. That equation, you have every single variable on the right side is a known. So you can plug in XF, 40, plug in XI, 0. T is, this is T final. Actually, if I want to be, this is change in T, which is TF minus TI, which makes that TF. But, okay, and then minus VF. Boom, we have all of the values. Now, if you don't want to do it symbolically, you don't have to. I usually just prefer to do it this way so that the teacher knows, hey, I set it up correctly. I did it right. If I got it wrong, it's because I plugged something in incorrectly. So I'm not going to plug this in. I'm going to trust that Jason's notes has the correct answer, which is 6.63. And I actually did it a little bit different than Jason. He didn't do it symbolically first. He plugged in numbers into one of these and then plugged numbers into the others and then solved for A and then put them together. So he never had a symbolic solution. But you can do it however you want. I just prefer the symbolic method. Now, the acceleration is now easy. If you have VI, you can easily just plug that in to this one. I mean, we already have A solved over here, so maybe this one would be a better one. But from that one, so VF 2.8 minus 6.63, that will give you a negative answer. Divided by T, 8.5. Once again from his notes, 0.453 meters per second squared. I hope I got all my sig figs right with 3 sig figs everywhere. That's another thing that's interesting about symbolic. If you can get a symbolic answer, you can plug all your sig figs in at the symbolic answer and it's still correct. You don't have to plug it in multiple times and hope that you're doing your sig fig calculations right every single time. So just be aware of that. So those are your two answers, VI and acceleration. This is negative. Come on, correct me. Any questions? Okay. I'll leave that up for now. Now that we're done with this point, wait, let me make sure. Oh, okay. So the one thing that we didn't do yet, so yes, this is negative, that makes sense. It falls in line to my prediction, which was very wide, but I mean, it still worked. My prediction was correct. It was in between -2 and 0. Yeah, just to give you an idea, -2 meters per second squared is pretty fast, but it's about half a meter per second squared. Then the one thing we need to do is make sure that the units make sense. So we're solving for this. VF automatically has the right units. It's meters per second because it's defined. X over T. That is also the definition of meters per second. So we have meters per second minus meters per second still equals meter per second. So the units, I literally did this on all my homeworks. I said units, check. So I'm like, yes, the units made sense. Okay, so now we're done. That's the finalized part. Okay, so I'll leave that up. So now we can move on to homework questions. Does anyone have any homework questions? Yes.
I also choose the first one with the race.
Let me pull it up. Which one was it? The one for today?
It was the homework that we do on Friday.
Okay. Okay. So problem 1 for the Friday assignment. Okay. Homework 2. View. The hare and tortoise one? Okay. So, let me make sure this comes up correctly. So hare, tortoise, in a race over a course 2.3 kilometers long. Has everyone got this? Can I erase it? Okay. Now I may, on homework questions, I may not give you the full answers if I feel like I'm giving you too much, because I don't want to just do the whole thing for you and give you the answer, but I want to make sure that you understand what's being asked. So we're going to go over like conceptualize and things like that. Okay, so you have a hare and a tortoise. They compete in a race. So here's X initial, X final. This equals, so the numbers are actually different as well. So 2.3 kilometers. We'll define this to be 0 kilometers. The tortoise crawls straight and steady at its maximum speed of 0.260 meters per second. So velocity, so it's steady, right? So velocity initial equals velocity final, which equals 0.260 meters per second. Now one thing that actually might make this simpler is to change everything to the same units. This is going to be, wait, what, it was 2.30 e to the 0.3 meters. So put everything in meters, 0 meters. Okay. The hare runs at its maximum speed of 14 meters per second for 0.8 kilometers and then stops to tease the tortoise. How close to the goal in meters can the hare let the tortoise approach before resuming the race, which the tortoise wins in a photo finish? So it means that they arrive at the same time. So both of them arrive at the end at the same time, but photo finish, tortoise wins, obviously. So the hare runs its maximum speed of 14 meters per second toward the goal, 4. So this is velocity initial, we'll put a little t. So that's tortoise. Velocity initial hare equals 14. That is cruising. It goes 14 meters per second. 14 meters per second. And then he stops. So one of the first things you need to do is determine how far did he go. Is that actually a question? How close to the goal in meters can the hare let the tortoise approach? So basically what this question is asking is saying the hare went at a steady pace of 14 meters per second for 0.8 kilometers. So I guess we already know how far he went. Then we need to know the time. So that's like somewhere around here. My scaling might be off, but so the tortoise went this far, which is 0.8, let's do meters, 800 meters. Went 800 meters, super quick. So 1400, so the first thing you need to do, how long did it take to get here? You need to determine time, what should I call this? Time 1 hare. So what does that equal? How long did it take him to get there? Then the tortoise is going to continue going until it gets to a point. At that point, this one right here too, this is going to be T2 hare. Oops. This time that takes for the tortoise or the hare to get from this 800 meter mark to the end would be the same. So the time it takes the tortoise to get here, this is going to be T1 tortoise. To get to some arbitrary point. This is the point we're trying to find out. And then he goes from there to the finish line. This is T2 tortoise. So they're asking to figure out, these two equal each other, T2H equals T2T, and they're asking you to figure out what that is. So how, no wait, you don't need the time. But from the time you can figure out the distance. So they're actually trying to determine what this distance is. Which you can do simple enough because the constant velocity of the turtle should be able to spit out a nice little x value. I don't know how much more I want to say. Does it conceptually make sense? Okay. Conceptually, you should, from everything I just told you, you should be able to get an answer. Some of the battle is sometimes figuring out what it's trying to ask. And so it's asking for the distance, but if you have the times and you know the constant velocity, you should be able to get that x value. Are there any other homework questions? Yes?
Homework is due Friday. Your last question, we have to find out what area are we trying to find.
Okay. You have to write your answer out on paper. Okay. In figure below, the area under the velocity versus time graph and between the vertical axis and time t represents the displacement. So that's velocity, yes. The area consists of a rectangle and a triangle. Compute their areas. So you're asking like which specific area you need to compute?
I guess now you read it.
Oh. Oh, if you did the conceptualized part, you might understand a little better. Yeah, so as shown, the area consists of a rectangle and a triangle. No dumb questions, though. All good questions. Because it helps us learn. Any more questions? There's 3 minutes till the end. Yeah?
Yeah, for this part, I have 8,800, and you're looking for the 3 significant figures from 8,800.
Yes, I believe all of them have 3 sig figs. Except this one that has 4, but it gets trumped by the 3.
Yeah, so if I have 8,800, how can I turn to 3 significant figures?
How much do you have? 8,800?
Yeah.
Oh, you're asking how